In the winter of 1936, the Soviet Union was racing to build the infrastructure of a global superpower. Thousands of miles of rail lines, massive canals, and industrial dams were being carved into some of the most hostile environments on Earth. But as the sub-zero temperatures arrived, the state faced a quiet, systemic catastrophe. The concrete was tearing itself apart from the inside out. When massive quantities of concrete are poured, a chemical reaction occurs. The curing process generates intense internal heat, sometimes exceeding 50 degrees Celsius. In the freezing Russian wilderness, this created a lethal gradient. The exterior of the concrete dropped to sub-zero temperatures, while the core remained scorching hot. The resulting thermal stress created immense tensile forces. Even when the concrete was poured during the height of summer, it cracked by winter. These weren't cosmetic flaws, they were structural death sentences for bridges, railway embankments, and megadams. To stop the destruction, engineers had to predict exactly how heat would dissipate through complex, three-dimensional structures before a single bucket of cement was poured. Mathematically, this meant solving inhomogeneous partial differential equations, specifically Fourier's laws of thermal conduction. This was an invisible, shifting field problem over time and space. You couldn't just solve for a single number. You had to calculate the temperature of thousands of individual points inside a wall simultaneously as the ambient weather changed around it. In the 1930s, digital computers did not exist. Mechanical desk calculators could handle basic arithmetic, but they were useless against a fluid, spatially distributed process like heat diffusion. For a single concrete design, a team of human calculators would have to spend weeks performing grueling, repetitive numerical iterations. By the time the math was verified, the concrete had already been poured and the cracks had already formed. Soviet engineering had hit a hard mathematical wall. Enter Vladimir Lukyanov, a young railway engineer working on the remote Troyetsk-Orsk tracks. Lukyanov had spent years watching this crisis unfold. He realized that if humans couldn't compute the equations fast enough with pen and paper, they needed to find a physical medium that solved the math automatically. In 1936, he noticed something profound. The way heat distributes itself through a solid wall follows the exact same mathematical patterns as water flowing through a network of pipes. Nature uses the same code for different elements. Lukyanov realized he could build a physical analogy of calculus. In his design, water level represented temperature, flow rate represented heat transfer, the thickness of the glass pipes represented the thermal resistance of the concrete, and the storage tanks represented the heat capacity of the material. He didn't build a computer to calculate numbers, he built a machine to simulate reality. Built at the Institute of Way and Construction, the first model was a masterwork of hydraulic engineering. To program it, the operator didn't type code, they adjusted a series of interconnected taps and valves. If a concrete wall was twice as thick on one side, the operator turned a valve to restrict water flow by exactly half at that coordinate. If the outside temperature dropped to -20, they adjusted the master reservoir to lower the hydraulic pressure. When the master valve was pulled, water rushed through the hydraulic network, seeking natural equilibrium. The pipes and tanks performed thousands of simultaneous calculations instantly through the pure physics of fluid dynamics. Within minutes, the water columns stabilized. By sliding a sheet of graph paper behind the glass tubes and tracing the top line of the water level, the operator was left with a perfect visual plot of the temperature curve inside the concrete. Plumbing solved partial differential equations in a fraction of the time it took a room of mathematicians. The invention was an absolute triumph. This wasn't a temporary prototype. The Soviet Union standardized these machines, entering serial factory production in 1955 under the brand name IGL. For decades, these hydraulic integrators were distributed to research labs across Poland, Czechoslovakia, Bulgaria, and China. They were used to design the foundations of rockets, calculate the thermodynamics of permafrost mining, and study the internal temperatures of the Antarctic ice sheet. In an era when early digital computers were massive, prone to crashing, and limited by primitive memory, Lukyanov's water computers ran continuously with zero electricity well into the 1980s. Eventually, the unstoppable march of silicon microchips rendered fluid computing obsolete. The analog tubes were drained, the valves were closed, and computing became an invisible process hidden behind flat digital screens. But the legacy of the water integrator remains etched into the literal foundations of the modern world. It stands as a testament to an era when human ingenuity wasn't confined to code, and when the most complex mathematics on Earth could be solved by simply watching water flow.